Helium then burns steadily in a core of ideal gas. The hydrogen burning shell is pushed outwards by the new luminosity of the core, which cools it down and reduces the nuclear burning rate and thus the luminosity. The temperature gradient drops accordingly, becoming subadiabatic, and the deep convection zone that made the star a red giant ceases. The star contracts and settles in the horizontal branch. So the star would go here, this is the tip of the red giant branch, is going to then settle in this region, which is the horizontal branch. So the star contracts and settles in the horizontal branch, which is the analog of the main sequence for helium burning. The horizontal branch is called horizontal branch because they appear at roughly constant absolute magnitude. Now, this is because even though the spread in luminosities in this branch is roughly the same as in the main sequence stars of same mass, the average of luminosity is much, much higher. So the horizontal branch stars are about like 50 solar luminosities. And because magnitude are a logarithmic scale of luminosity, the same degree of linear dispersion at a larger decade will appear more constant. If you plotted this in linear, so in luminosity, you'd see pretty much the same scatter in the horizontal branch as you'd see in the main sequence. So this is what happened to the star. The star had the helium flash and then jumped to an ideal gas again, where you have stable helium core burning. And this is the structure of a horizontal branch star. You have helium burning in the core that is depositing inert carbon and oxygen in the center that builds up. You have a shell around here, which is inert helium. And then you have a hydrogen burning shell and the inert envelope that is not burning, the hydrogen envelope. In the HR diagram, the star settles in the horizontal branch, which is essentially the helium main sequence. Now, once helium is exhausted, an inert core carbon ash is left. Surrounding it, you have a helium burning shell and a hydrogen burning shell. During shell burning, the core has zero luminosity. And the situation is thus very similar to the hydrogen burning phase. And as you exhaust the hydrogen and you have a leftover helium ash, and then this helium ash is contracting, and the star climbs the red giant branch as a result, the same thing is going to happen here. The star is going to climb the red giant branch again, and it's going to become a star of the asymptotic giant branch. The carbon-oxygen core contracts and heats up. You have a phase where helium is being burned in a shell around the core. So this is the helium burning shell. And then after that, you have the hydrogen burning shell and the hydrogen envelope. From the outside, if you plot in HR diagram, what you're going to see is that the star is climbing again the red giant branch. It's going from the horizontal branch and it's climbing again here the giant branch. Now it's called the asymptotic giant branch. In this final stage, the star is very unstable, having thermal pulses. As a hydrogen burning layer ignites and then dumps helium ash on the helium layer underneath, the mass of helium increases and making it slightly degenerate. What you're looking here is time and the luminosity. This is the same plot. This is just continue here. You have 10 here and you have 12, which is time in 100,000 of years. So 10 is about 1 million years. And this is the time between the pulses. Again, these pulses happen because you have hydrogen that is burning, and then it is depositing helium ash in the layer below, making it slightly degenerate as you increase the density. And then when the temperature at the base of the helium layer increases sufficiently, a helium flash occurs in the shell. The helium flash drives the hydrogen shell outwards, which cools the star and turns off the hydrogen burning for a while. As the helium is consumed in the triple alpha, the star contracts, heats up again, and the hydrogen shell then ignites again and dumps helium ash on the helium layer, and the process repeats in these thermal pulses. This is a series of helium flashes occurring at the helium shells, on the helium burning shells. So these thermal pulses are essentially a series of helium flashes. Eventually, as a star heats up, the last helium flash produces enough energy to blow up the star, ejecting the planetary nebula. So the planetary nebula are the gracious death of low-mass stars. That's when the last helium flash has enough energy to eject the outer layers of the atmosphere. This is another planetary nebula and another planetary nebula. What is left in the center is what is called a white dwarf.